Is Wednesday, March 26th. This is CS 746, Perspectives in Data Science. Today we're going to talk about clustering. Before I get started, I'm going to apologize for not having the exams ready to talk about. Found out there's one more person that was not feeling well on the day of the exam, and they still want to take that. And I'm going to be lazy and present them with one of the exams I already used. So I'm not going to show you the answers yet. I did look at the scores. Everybody in this section got the first question wrong. Why? Because the professor marked down the wrong answer on the rubric. So you all got a point marked off on the first question because the answer I'd marked wrong. The incorrect answer I marked was plausible enough that the GTAs went and just graded it right up and went through and says, okay, we give everybody partial credit. So everybody got 1 point for the first question instead of 2 points. Anyhow, scores are wildly all over the place. Some people did just extremely well. Other people, didn't do so great. So it's definitely going to be graded on a curve on there. So we'll get down to that and get figured out what's going on as we go forward. So that's our brief discussion of what's the state of the grading is for this class. Don't ask me about the state of grading for the other class. All right, clustering. What is clustering and why do we cluster? Right? Clustering is basically designed to segment your data into small subsets that you can treat similarly. I'm not mirroring my projector, am I? There we go. All right. So we want to take our cases and drop it into subsets. We're segmenting it into smaller pieces. We're trying to get a more compact description of a data set. We're trying to basically compress our representation. We're trying to model an underlying process that generates the data as a mixture of different localized processes. We're basically trying to find structure in our data. And the cool thing about clustering is it will find structure in our data, even where that structure does not exist. Right? So I could apply a clustering algorithm in this class and say classify everybody into tall, short, or medium, and it would do it, even though the difference between the tallest person in the short group and the shortest person in the medium group would be, 2 millimeters or something like that, right? But clustering will do that, right? Again, we got two different kinds of learning that we use in data science and machine learning and artificial intelligence and all that. And there's supervised learning where we have patterns in the data that we've already labeled, and we're training the model to recognize the patterns that we've already said are there, right? So we see how we evaluate our model on how well it matches the predefined labels. And then there's unsupervised learning where we don't have a target attribute that we're telling it to classify on. And we want to explore the data to see if there are intrinsic structures in them, or if we can, be a political commentator and find structures in the data where they don't exist. That was not a politics joke. That was a political commentator's. The machine learning task of inferring a function, unsupervised learning, to describe hidden structure from unlabeled data is called unsupervised machine learning. There is no class or category that's included in our data. In a second. There. Turn that front light off so you can see the screen better. Okay. Clustering is a technique for finding similarity groups in the data. We're going to call those clusters because it's an original word. It groups the data in instances that are similar to each other in the cluster and data instances that are different from each other, that are far away from each other into different clusters. It's called an unsupervised. There's no values, a priori labels or anything like that. For historical reasons, because for a long time, the power of our computers was such that we couldn't do really heavy-duty algorithms and massive floating point calculations and things like that, right? So clustering is often considered synonymous with other unsupervised learning. In fact, there are other kinds of unsupervised learning, and there are probably new types being developed every day because there's a lot of active research going on. Association rule mining is an unsupervised technique that's been around for a while, and people just kind of ignored it for a while, right? So illustration, here's our data represented in 2 dimensions. Well, obviously, there are 3 natural groups of data points in there, natural clusters, right? That data is naturally divided itself up into clumps. So we can obviously just, eyeball it and say, yeah, we got 3 clusters, 1, 2, 3. We could go and focus in closer and say we could make some smaller, finer structure, make smaller clusters. But there's obvious ones that are the first glance, right? Why do we cluster? Because having a person sit down and label the data is expensive, right? You have to feed people. Right? So they demand money so they can go to their favorite restaurant, have food or something like that, right? So they demand a paycheck. We want to gain insight into the structure of the data. Maybe we don't have any experts on this data. We want to see if there's something there that no one happened to have noticed. Experts overlooked it, right? We want to find prototypes in the data, things that we can start labeling, right? So let's see some real life examples. Okay, if we order T-shirts, they came in and had some WSU School of Computing T-shirts they were passing out a while ago. They asked you, what's your size? Right? And you tell them small, medium, large, extra large, so on and so forth. You don't tell them, so many inches around the neck, so many inches around the chest, so on and so forth, right? Tailor-made T-shirts are just too expensive. One size fits all does not work because people come in different sizes, so they just kind of do groups. In marketing, when a company wants to market to different customers, obviously, if they could tailor the solution that they're selling precisely for every individual customer, that customer would be very happy and would pay significantly more money for the solution that perfectly meets their needs, right? In reality, the company has to make money. It can't be spending all its time doing research into the customer, so it segments the market into different groups. And we have, banking segment, we have the farming segment, we have, lawyers, things like that. And so on and so forth. And we can do targeted marketing to those different segments of the market. Another example, we have a bunch of text documents. We want to organize them according to their content similarities. Maybe we want to produce a topic hierarchy. Maybe we want to look for cheating. Maybe we want to see how many people appear to have used ChatGPT, right? Maybe we don't care about that too much. We'll see, right? But, these are kind of things that people want to do with clustering, right? So if we can go out there and take a whole bunch of papers and throw them all into a bucket and find that the things that we generated with ChatGPT all have a kind of a similar look and feel to them, then we can use unsupervised learning to detect people who've written their English essays using ChatGPT instead of sitting down and doing it themselves or having their next door neighbor write it for them, right? In fact, clustering is one of the most utilized data mining techniques. There's a long history of clustering. Almost every field, from medicine, psychology, botany, everything, biology, archaeology, marketing, insurance, libraries, et cetera, et cetera. In recent years, text clustering has become much more important, right? So, again, the most straightforward and obvious kind of topic hierarchy is you go to the library over here at Abla Library, and you want to find a book, and there's a library call code for it, right? And it tells you where that book is. And all the books that are in that section are all on the same topic. And you can look around and find other things that are written about the same subject, right? So useful. Given the goal of clustering, we want to find our data points. We want to be able to define our cluster such that the within cluster similarity is maximized and the intra-cluster similarity is minimized. So, these two groups are far apart. We want to make sure that we cluster them according to these natural groupings rather than trying to make, a group here, a group consisting of the middle, and a group over on the right side, right? Try to cluster this into 3 groups. We won't succeed very well, right? Now, in order to do this, we need to have some sort of a similarity measure. So, well, it's time for The Simpsons. What is a natural grouping of these objects? These slides are stolen from this fellow named Eamon Kyo, who apparently made all this stuff available for everybody several years ago. So it's great. So what are the groups that you can see in here? Anybody? Male, female, that's an obvious one. What else? Old, young? Yeah, members of the Simpsons family. Homer, Marge, Bart, Lisa are members of the family. And Grandpa, what's his name again? Anybody watch The Simpsons? something. Grandpa, anyhow. And then we got school employees that work at the school that Bart and Lisa go to, right? So there's all these different kind of groups. I love this. When I first got this slide, someone had put 10 years ago. I crossed it out and put 20. And then after a couple of semesters, I says, maybe it's even longer ago than that, right? Families once looked like we had this concept in the US of a nuclear family. Mom, dad, 2.3 kids precisely. I don't know how I had a third of a kid, but anyhow, that was the average family in the United States. It's different now, right? Nowadays, clustering is subjective, right? We can do it with Simpson's family versus school employees. We can do it as males and females, as we said. And we can do, short people, tall people, whatever. There's all sorts of things, well-dressed, poorly dressed, rocking out, or, whatever, right? Similarity is hard to define, right? But you know it when you see it, right? I mean, obviously those people aren't, stuff, they're not, but boy, those pictures sure are similar, aren't they, right? So again, you know it when you see it. We can have spurious similarities. We can have real similarities, right? Do people look like their dogs? Some folks say so. I don't think I look like any of my dogs, so oh well, there we go. Defining a distance metric. We really need a metric for this, right? So let's go ahead and say object one, object two, or two objects. And we'll say that we have some sort of a metric. And the distance is going to be the dissimilarity, how many changes you have to make to get from one object to another. We'll call that D from O1 to O2. So two fingerprints, what are the differences between these fingerprints? Two names, what are the differences between these names? How many letters do we have to flip? How many letters do we have to delete and re-add? Different metrics we can use there, and of course there's, chimpanzees and gorillas, how much difference is there between those? We have to look under the hood at the DNA to see what the differences are, right? What should a distance metric do for us? Well, it should have some properties to make it a useful metric. The distance from A to B should be the same as the distance from B to A. This is symmetry, right? There's a highway in Arizona. If you drive from Phoenix up to Payson and then turn around and drive back from Payson to Phoenix, the distance is different because they built one leg of the freeway one direction, and then several years later they came back and built the other one. They didn't have any room. They had to make it, jog around and zigzag a little bit, right? So distance on a freeway isn't always a great distance metric. It doesn't have similarity or symmetry, right? Constancy of self-similarity. The distance from A to itself should be 0. That seems pretty obvious, right? Positivity. The distance from A to B should only be 0 if A and B are literally the same thing, right? And finally, triangular inequality. We have A, B, and C. The distance from A to B should be less than the distance from A to C plus the distance from B to C. Imagine we got 3 points. They should be like in a triangle where if you go from, or less than or equal, right? If you go from point A to point C to point B, you should not be able to make that a shorter distance than going directly from A to B, right? So basic geometry should hold. The intuitions behind these. Symmetry. If symmetry didn't exist, you could claim that Alex looks like Bob, but Bob looks nothing like Alex, right? Distance from A to A, constancy of self-similarity. If that did not exist, you could say that, Bob looks more like Alex than Alex does, or Alex looks like, whatever, read that wrong. Anyhow, but, you've got something that looks more like you than you do, right? Which doesn't make sense. Positivity. If your twins are so precisely the same that you cannot tell them apart, right? Even if they're standing in the same room, they seem to merge into a single entity, something like that. Weird, fantasy novel type stuff, right? There are objects in your world that are different, but they're impossible to tell apart. Even with twins, we can tell them apart. We can put them right next to each other, right? We may not know which is which, but we can tell they're two different objects, right? Two different people. Triangular inequality, you could say that Alex is very like Bob, and Alex is very like Carl, but Bob is very unlike Carl. It would be nice if the A's, B's, and C's lined up here, but anyhow. But this is actually the letters rearranged. But the whole point being, if I take path through a third point from A to B or from A to C, that third point should not give you a shorter path than going directly from A to C, right? So that's what we need for our metrics, right? And we can define all sorts of metrics, right? If we're doing text work, we can define a simple metric called the Hamming distance, where we just say however many letters you have to flip to get from one string to the other, right? Or we can define the Levenstein distance, which is how many letters you have to delete from one string and then add back in to create the other one, right? So on and so forth. So there's two types of clustering we can do. Partitional and hierarchical. Partitional is we say we've got all of our stuff. We find some characteristic. We just split down according to that characteristic, right? Here in this case, it says, are these members of the Simpsons family or are they school employees? We just drop them into a bucket, right? Hierarchical is we create a hierarchical decomposition. We create a tree, right, of the objects using some criterion. And then in this case, we can like decide how many clusters we want by choosing at what level of the tree we stop chopping things apart, right? So the desirable properties of our algorithm, we want it to be scalable, right? If our algorithm is order of n squared runtime, the bigger our data set, you know, the combinatorial explosion happens and our algorithm runs for longer and longer with the bigger data sets until, you know, you get to a certain size and it's just running, you know, ridiculously impossibly long runtimes, right? So you want to be able to scale it. You don't want to take up too much memory space either, but you want to be able to deal with different kinds of data types, right? You don't want to be just limited to only doing arithmetic calculations on numbers. You want to be able to find a way to code things, you know, different characteristics such that you can calculate your distance metric. Of course, in a computer, everything is a number, right? But you need to find a way to have that number mean something. You want to have minimal requirements for the domain knowledge. You don't need to want to be able to preload this model with, you know, the knowledge of how the entire universe works, right? You want to be able to deal with noise and outliers. You want it to give you the same output if you feed the data front to back as if you feed it in front back to front, right? Or if you scramble the data up, you'd like to get the same output from it. You want to be able to incorporate constraints that the user might want to place on it, right? The user might say, you know, I know these things look similar, but they're not really, so ignore that particular metric, right? You want to be able to interpret and use the data that comes out of it, because what's the use of a completely opaque model that no one can understand, right? So a useful tool for summarizing similarity is what's called a dendrogram. There's in biology, there's a term called the cladogram, which is the same thing. You've got a root where everything assumes to have, you know, started with our maximal dissimilarity, as it were. We got internal branches, internal nodes. When a node ends a leaf, it's considered a terminal branch. So it's a tree, right? And the similarity between two objects is represented by the height, the lowest internal node that we share, right? As Eamon Keough says, there's only one data set that can be perfectly clustered using a hierarchy, and that is the tree of life, right? And in the theory, we have evolution says that everything evolved from simpler creatures, and so, you know, we have things that are more similar to us and things that are less similar to us. Of course, don't look too closely, because if you look too closely at the tree of life, you find out it's not really a tree at some layers. So, you know, this is a classic example of oversimplifying, right? But it is true. We can take all the large animals that we see, you know, every mammal, we can see a kind of a, you know, different distance metric. Looking at the DNA differences under the hood, we can see how closely and distantly related things are, and we can assign a useful metric to that. All right, other hierarchies exist. Famous one for years was Yahoo, which was like pre-Google, pre-ChatGPT, free Microsoft, any Copilot, anything like that, right? And this was, they actually had people in a room that were out there looking at websites. And they'd say, this is a computer games website. And this is a bookstore. And this is information about state parks in Kansas, and so on and so forth. And they'd look at every website and they'd say what it was about. And they built themselves this like library-like hierarchy of things, manually created, right? Back in the day. And I believe, if it might still be out there. I don't know. Is anybody using it? Probably not. Right. But for years, this is a place where people would go. They go to Yahoo, search what they were looking for. It would take them right to it. Sometimes we can see meaningless or spurious clusters in here. So for instance, we're looking at flags. We're trying to do a clustering algorithm on flag similarity. So we're going to look at the colors, the shapes, the number of stripes and stars and things like that, and find things like, well, look at this: Australia, St. Helena, Anguilla, South Georgia, and the South Sandwich Islands. They all have this same, St. George's cross that the UK flag has. And well, it makes sense because those are all former colonies of Great Britain, right? In fact, some of them still are colonies. St. Helena, South Georgia are still colonies of UK, right? But we look at Niger and India. When you think, well, those flags look pretty similar. I wonder if Niger and India somehow were like linked politically in the past, right? And the answer is no. That's a completely spurious grouping, right? The flag in Niger is orange over white over green with an orange disc in the center that symbolizes the sun. The orange is the Sahara Desert. The green is the grassy plains of the south, and the river Niger, which sustains them, so on and so forth. White symbolizes purity and hope. The Indian flag is a tricolor with deep saffron on the top, white in the middle, and dark green at the bottom. In the center, there's the Dharma Chakra, which is a wheel of law that dates back to the 2nd century BC. So incredibly deep history there, right? And the symbols, the colors, white stands for purity and truth. Similarity there. Green for growth and auspiciousness. Well, I guess grassy plains can be, there's some similarities behind the flags, but they were not created by the same person anyway. This is just a spurious grouping, right? So we've got to be careful in our clustering algorithm to recognize that the computer doesn't know when it's found something that's spurious, right? Of course, as our AI gets smarter and smarter, we'll eventually be able to teach it about things like that. But then it'll be like, will it still be unsupervised learning, or will it just be computer supervised, right, by that point? So using a dendrogram, we can determine the correct number of clusters. If we start drawing our vertical lines longer and shorter in our dendrogram to show the actual distance between the points, right? So we start over here on the blue side, and we'll find the 2 closest or 3 closest points, maybe a cluster right here, and those are in a little group here in the dendrogram. It's bigger and bigger, and eventually we see this large jump in our dendrogram. And we see that big jump, we say we found a natural clustering location. So it's easy for our algorithm to see these big changes in the distance metrics, right? But what do those distance metrics mean, right? Also, if we see, in this case, if we have an outlier in our data, we'll see some branch that's got a single isolated item in it, right? With a huge distance metric from everything else. So that is another way to detect outliers, right? Is you use a clustering algorithm on it. So how do we do a bottom-up or a hierarchical cluster? Well, we got 2 different ways to do it, right? We could do bottom-up. We could do top-down. We could, look at the number of dendrograms with n leaves, 2 to the n minus 3 factorial over 2 to the n minus 2 to the power of n minus 2 times n minus 2 factorial, right? So you got a bunch of factorials and exponentiations in this thing. So your numerator goes up tremendously quickly. If you have 2 leaves, there's only 1 dendrogram possible. If you have 3 leaves, there's 3. If there's 4 leaves, there's 15. By the time you get up to 10 leaves in a dendrogram, there's over 34 million possible ways to arrange that tree, right? So you're not going to do an exhaustive search on this because this algorithm scales poorly, right? So we can start bottom up or top down, where we start with every item is its own cluster. If we have 1,000 items, we have 1,000 individual clusters. We find the clusters that are most similar to each other. We put them together. We put them together until we build up to the top. Or we can start at the top in a single cluster, consider every possible way to divide into 2 pieces, choose the best one, recursively operate on both sides. So we have to start with a distance matrix, which contains a distance between every pair of objects in our database. And again, we still haven't discussed what is the distance metric we're using, right? But we'll just assume we've got something here, right? And the distance metric between anybody, any character and their self is obviously going to be 0. The distance between these 2 characters, you can say, is significantly different, right? Why? Well, because we defined our distance metric that way, right? We'll get into that on the next slide. Next 3 slides in the future, I guess. So we're going to do bottom up agglomeration. Let's get this out of the way here so we can start on the bottom. Consider all the possible merges, choose the best. Well, on the previous slide, we see that our lowest distance metric on that we've chosen has a distance of 1 here. There's a 2 here, a couple of 3. So we're going to take the best one and combine those 2 twin sisters, right? And then the second one, distance metric is 2 between these 2. Then we combine these 2 groups together, choose the best at all levels. We continue just merging in the shortest distance between these groups until we have a full hierarchical tree. Okay. So we know how to measure the distance between 2 objects, though. The problem is we're trying to combine clusters, right? So what is this distance metric between this group and this group, right? So we need to find some distance between an object. The distance between 2 clusters is not obvious. There are 2 different ways to do it. There's single linkage or nearest neighbor, where we have a cluster. We find the 2 objects, the one in cluster 1, the one in cluster 2, find the 2 objects that are most similar to the closest object in the other cluster. And we use that as our metric, single linkage, the nearest neighbor. Or there's complete linkage, right? I'm sorry, there's 3 different ways to do it. And this is furthest neighbor, or farthest neighbor. The distance between the 2 clusters is to determine the greatest distance between any 2 objects in the different clusters. So again, we've got a blob over here, we've got a blob over here. We find the 2 that are farthest apart, right? Or the third way to do it is the group average linkage, where we calculate the averages between all pairs of objects in the 2 clusters. So of course, we can be lazy. We can calculate the centroid of each cluster, right? And that gives us the average location in the middle of the cluster. And now we can go ahead and calculate those 2 different points, right? So that's a way to get the average linkage, a little bit less computationally expensive, right? But you know, in general, those are our 3 ways to do it. You know, find the 2 closest things between the 2 groups, find the farthest ones, or find the average. So here's our example of if we tried to use single linkage, where we're using the closest in every case, or the average linkage, where we're actually comparing everything against everything else, or comparing the average center, the centroid of each existing cluster to the other ones. Here's our single linkage. Here's our average linkage. Which one's better? Well, this one's clearly better because they put numbers on the axes. That's a joke, right? You can do it either way. It doesn't matter. The default is to use average linkage because it seems more robust to people. So there's no need to specify number of clusters in advance when you're doing hierarchical clusters. You just build your hierarchy, and then you say, well, what looks like a good place to split this hierarchy, right? Where's a good clustering to put on it? The hierarchical nature maps nicely onto our human intuition. We think about, things by classifying them, right? It doesn't scale well, though. The time complexity is of order of n squared, where n is the number of total objects. So if you have too large of a data set, your hierarchical clustering is going to take a very long time to run. Like any heuristic search algorithms, where you're going out there and just looking for the shortest distances, you can end up doing what's called hill climbing, where you get into a local optimum, right? And you get stuck in the wrong place. You haven't found the best solution. You found a decent solution, but not the best one. Finally, the interpretation of the results is pretty subjective. What does this actually mean? It's not really clear in all cases, right? Finally, we're finally at the slide where we say, well, how do we measure similarity? And the answer is, well, we measure similarity by counting dissimilarity, right? We've assumed that we have one. We've even got numbers down here at the bottom of the slide, make it look all official and everything, right? And we can infer what some of these numbers mean. If we take Peter and Piotr, right, we have to flip, we have to rearrange these three middle letters, right? And we've changed three letters to get one word to change into the other. So that tells us this is maybe a Hamming distance that we're doing here, right? Well, a generic technique is, just like we did there. How do we turn one thing into another? So, of course, this is named Marge, and this is her sisters, Patty and Selma. In order to change Patty and Selma into Selma, we'd have to change the dress color. That's kind of absurd, right? We have to change the shape of their earring. We have to change the way they part their hair, right? And so I'm looking at this as just a picture, an image, right? Those are the three different things. We could talk about flipping the image, but we're generally going to say that, we're not going to count that as an actual change, right? In order to change the distance between Marge and Selma, on the other hand, we have to change the dress color. We'd have to add earrings. We'd have to shorten her. We'd have to have her take up smoking. We have to have her lose some weight. Maybe, I don't know. It's hard to tell in that case, right? But the distance between Marge and Selma then is 5. The distance between Patty and Selma is, we're going to call that just 3, right? So that's the edit distance. How many edits do we have to make to this image to change it into this image, right? And of course, we have changed the hair, and so on and so forth is also in there. We don't have everything listed because it's just a slide in a presentation. So if you find out, that's not a mistake, it's just being lazy. Okay, so the edit distance example with words. If we've got any string Q, we can change it into string C using only insertion, deletion, and substitution. The similarity between two strings can thus be defined as the cost of the cheapest transformation from Q to C. So changing Peter to Piotr, we substitute an I for an E, we insert an O, we delete the E, and we've changed one into the other. Or we could just delete the 3 middle letters and add 3, right? In their place, depending on what kind of metric we want to use, right? So the distance here is we do one substitution, one insertion, one deletion. And we can build up a hierarchy, all these different flavors of the name Peter in all these different languages, Pierre, Pedro, Pietro. Actually, this one, since I'm from South Dakota, this is pronounced Pierre, because that's the name of the capital. And it's not actually Pierre. But all these give us a nice straightforward metric. It's easy with strings. It's easy with binary. How many bits did I flip in the message, right? When you're doing images, it gets harder, but you still have to represent it as some sort of a numerical metric, right? So partitional clustering, on the other hand, is non-hierarchical. Each instant is placed in exactly one of k clusters that don't overlap. Since the only one set of clusters is output, usually we have to tell it in advance, I want 4 clusters. I want 5 clusters. We have to experiment with the number of clusters. We have to see, does our model look funky when we create, only 2 clusters? If we create 17 clusters, does our model take too long to build? Things like that, right? So what are we doing? We got to have some sort of an objective function. We're going to use the Euclidean distance, Pythagorean distance. We're going to use the squared error. And we're going to say this is the centroid or the medoid of the group. And we're going to calculate the Euclidean distance to that. We're going to sum that all up. We're going to minimize that. And that is our simple k-means clustering algorithm. So the k-means clustering algorithm is a intra-cluster measure only, equivalent to the sum of the item to centroid kernels, right? So you've defined this as a cluster. These are all the groups in it. You've calculated where the centroid is. You're trying to minimize that distance. Lloyd's algorithm, simple greedy algorithm that locally optimizes this measure. For each item, find the closest cluster center, assign it to that cluster. So we basically, with random clusters, centers, we recompute the cluster centroid as the mean of the items that are assigned to that centroid. And then we see if the centroid's moved, right? The algorithm again, we start by saying how many clusters I'm going to make. We initialize k cluster centers. We can use completely random numbers if we want to. We decide the class memberships of every one of our objects by assigning it to the nearest cluster center. And now that we've got everything into a cluster, we recalculate where our clusters are by assuming that the memberships we found in step 3 are correct. And then if we now find that objects have changed membership in the last iteration, we go back to step 3. If nothing changes this group membership, we say we're done. We can pick our cluster centers by sampling the input data. So here's some slides where we're going to go ahead and start by kind of illustration of k-means clustering. So we'll start with 5 clusters. Here's our data. We assign all of our data points in this massive cloud of data to whichever point that data is closest to, right? We'll go ahead and assign it to that particular mean. And now we recalculate the centers, or the old ones are the plus signs right here, and the new ones are the dots. And now we go ahead and reassign things to the new centroids. So the stopping criterion is either no reassignments to data points or minimal reassignments, no or minimal change of centroids, or the sum squared error, that is the distance from all of the data points in that cluster to the center of the cluster. And that sum squared error, we're trying to minimize the decrease in sum squared error, right, below some threshold. So an example, simple graph. We've got these data points here. We'll go ahead and initialize 3 random centers, k-means clustering. We find the distance. We say, well, this one obviously is in K3. This one is obviously in K2. This one is obviously going to be in, not sure, right? We'll calculate. We'll assign labels. So according to the slide here, this one ends up in K1, this one in K2, so on and so forth. Now we calculate based on what the actual data is. Most of the data points in group 1 are over here, so K1 moves significantly to the right. Most of the data points in group 2 are down over here, so K2 moves down into the left, and K3 is going to move up into the right. So now we calculate what group each of these dots is in. This one here is now closer to K2 than it is to K1. This one here looks like it might be closer to K3, right? So we've changed membership on a couple of these dots, right? This one here moved from K2 to K3. Now we recalculate where our centers are. Everything moves a little bit. Now we see, does anything get reassigned? And the answer is no. Nothing is assigned to a different group anymore, right? So this means that our algorithm is finished. K-means clustering is relatively efficient, where it's on the order of TKN. We're given n objects, K clusters, and T iterations, right? It'll be a factor of those three things. Normally, since K and T are significantly less than N, is basically order of N, right? So our algorithm usually often terminates at a local optimum. Weakness, we have to have some way to define the mean of a cluster. If we're doing categorical data, right? Well, we'd have to use K-modes clustering, where mode means, of course, the most common value. We could do that, right? It's not as effective as K-means clustering, but we can do that when we don't have actual numeric data. We only have categories. We need to specify the number of clusters in advance. If we have noisy data and outliers, K-means clustering has trouble with those outliers, right? We can deal with outliers sort of by adding more clusters, and then our outliers end up in their own clusters all by themselves, right? If we have clusters that don't have what we call a convex shape, so if we have a banana-shaped cluster, right? K-means clustering is not going to identify easily a banana-shaped cluster in the data, right? So we'd have to do some, recalculation of axes or data transformation to be able to do that. How to do that? How to figure out how many clusters to use? Well, we use our scree plot from last lecture, or we're going to call it an elbow plot now. The idea behind the elbow method is to identify the value of K where the distortion begins to decrease most rapidly. So if we plot the intercluster within cluster sum squared errors, the distortion, how far away all the data points are from that center, right? The more clusters we make, obviously, the more centers we have to be closer to. So the less the distance to the center is. So for instance, if we take a bunch of data points and we say K equals 1, we put them all in one big cluster. In our distortion, the total distance squared error from every data point to the center of the data is on our metric 700 units, whatever they are. If we go to 2 clusters, it's down below 300. If we go to 3 clusters, it's down below 100. 4 clusters, 5, 6, 7, don't get too much better, right? So we're looking for that bottom of the cliff, right? Looking for the elbow in the curve. And there's generally going to be at least 1 or 2. There's either an obvious candidate or there's only 2 candidates to choose from when we get down to there in most cases, right? So in this case, we'd say we're going to use 3 clusters. So we have to run it multiple times. So that's where our K-means clustering, it's a little less efficient because we have to actually run it multiple times to figure it out. Now, one of the issues with K-centroids clustering is that it's not necessarily robust to noise, but we can make it more robust by using what we call K-medoids. And a medoid is, of course, instead of the centroid of the objects, we take a point from the data, right? So the centroid is obviously a point that we calculate based on the data, and the medoid is the point that is closest to that centroid. And so we fix our cluster center not at a calculated value, but at the actual data point closest to that, who's most centrally located in the cluster, or whose average dissimilarity to all the other objects in that cluster is minimal. And this is more robust to noise because tie it to actual bits of the data there, right? Another one that came along was partitioning around medoids from 1987. Starts from an initial set of medoids, iteratively replaces one. So it literally is looking at the data points in the data, and it says, well, I'm going to try to move to a different point or a different point. I'm not recalculating centroids. I'm just saying, if I go to the second closest one, what happens, right? See if it improves the total distance of our resulting clusters. This doesn't scale well. It's very effective if you have a small data set, though. Nearest neighbors clustering, which should not be confused with nearest neighbors classification. We'll get into that in the future lecture, but just know that there's nearest neighbor is just a statement. It's not a description of a specific technique. It's just a description of using the nearest neighbors for some purpose, right? And basically, we define a cluster, centroids, and we just start adding things one at a time to those clusters. Iteratively merge them into the existing clusters that are closest. We have a threshold T that's used to determine if items are added to existing clusters or if we're going to create a new cluster, right? How did we measure similarity? We had a distance metric, right? What distance metric did k-means use? It used Euclidean distance, Pythagorean, right? What assumption is it making about the data? That there are natural clusters in that data, right? So let's try this partitioning algorithm to define clusters. And so what we're going to do is use the nearest neighbor clustering, right? So if we set a threshold, instead of saying I want 3 clusters, we say I want to make as many clusters as you can where nothing is further than 0.3 distance away from its cluster center. I'll end up with one big cluster. And everything will get added in, and we got all the the linkages shown here just to show that they are clustered. If we set our threshold lower, say that things have to be, and again, we're on a scale of 0 to 1 on both axes. We've renormalized our data to scale 0 to 1. If we say our distance threshold is 0.1, and of course we'll form groups where nothing is in a group with any, the distance in the group from one end to the other can be significantly bigger than 0.1, but it's always got something that it's within 0.1 distance of. Obviously, if I create a distance of 0.3 threshold, I'm going to get a lot of very small groups, right? So this is a way to generate natural clusters if they exist in your data. You can help use or discover what the clustering are. Should we use Euclidean distance? It's important to recognize that you have to scale your data correctly. If we take our scaling, which is isotropic along all directions, and for instance, we double the horizontal or the vertical axis and halve the horizontal versus doubling the horizontal and having the vertical distance, you can see that we'll get different cluster groups, right? So these are all the same data points, just scaled, stretched in one direction, squished in another, right? And so the issue here is that if our data is isotropic, we can do this clustering technique, but it's not invariant to linear transformation. Any transformation that distorts our distance relationships is going to change the clusters that are generated by this algorithm. So is normalization desirable? Well, yes. Right. We have it unnormalized. We have significant differences in the x-axis. If we normalize everything so the x and the y are the same, we'll see that the differences in the y-axis are important, and we'll be able to pay attention to those a little more easily than if we have unnormalized data, right? So some other distance metric we could use. We could use what's called the Minkowski metric. We define the distance from x to x prime, or the distance is bigger than or equal to 1, or the metric is bigger than or equal to 1. We take the distance, the absolute value of the difference raised to the power of q, and then take the qth root on the outside. And basically, this is kind of a general function for spatial metrics. If we have use a Q of 1, we basically have what we call the Manhattan district, where you have to walk either orthogonally east-west and then north-south and measure your distance that way. If you use Q equal 2, we end up with the Euclidean distance. Use q equal 3. We can get into higher order dimensions, things like that, right? We can also use another distance metric here using the cosine of the angle. Treat each of these as a vector, and we calculate the cosine between the two vectors of the points, right? And that gives us another kind of similarity function. There's other things we can do, right? When features are binary, this becomes the number of attributes that are shared by x and x prime divided by the geometric mean of the number of attributes in x and the number in x prime. Simplification, the distance from x to x prime is x transposed times x prime over d over d. Blah, blah. Yeah. Okay. Now it's important to know that we have what we call a cluster bias. We see clusters, whether there's cluster structure there or not, right? We try to cluster things because it makes it easier for us to understand. We have what we call exemplars or Pythagorean or Platonic ideals, right? From the ancient Greeks, there is an ideal dog. It's, of course, the dog I own, whatever I happen to own at the current time. It's the ideal dog, right? But we see structure and we see different breeds of dogs, right? And we can cluster them according to the breed. This works pretty well for dogs, but when we start doing some things that are a continuum, again, here's a list of someone tried to classify or cluster the movies that were available on Netflix way back in 2007, right? And it says, well, we'll go ahead and classify these as all documentaries, and we'll classify these as sports movies, and here's some IMAX movies, and so on and so forth. And we try to draw these clusters, and it just turns into this big old mess, right? So this is a continuum, and trying to do clustering, classification on a cluster, on a continuum is not easy and can lead you to invalid conclusions. So k-nearest neighbors and factoring models do a lot better than discrete cluster models when you have a continuum. Upshot, we use clustering more than we should. Why? Because we just assume that everything has a cluster in it because we're humans. There's a famous thing called the Myers-Briggs personality type. I just happened to bounce across someone using this the other day. I was looking at a story online, and they ended up at the end of the story, and they says, okay, I've got the Myers-Briggs types for all the characters in here so you can understand why they do what they do. Well, Myers-Briggs is asking someone to describe how they're feeling at the moment, and then you're assigning labels based on what they're told you their labels already are, right? So it's kind of, continuous data underneath. They do not fall into these simple groups, ENTP or ISTJ, that they use in Myers-Briggs. We're on a continuum between these different types. Just with Netflix, continuous models, dimension reduction like PCA, k-nearest neighbors, those tend to do better. So last slide, then we'll do a quick stop on an example for you to look at. Sounds like you're wrapping up something. I am wrapping up something, yes. Wrapping up this lecture. Man, that was a smart, okay. That reminds me of Clippy back in the bad old days. Anybody know what Clippy was? Microsoft tried to come up with this assistant thing. It was the dumbest, little animated paperclip was what Clippy was. And, sometimes I'm too old. Yeah, that's it. Yeah. Anyhow, hierarchical clustering. We form a hierarchy. We can calculate it bottom up or top down. Flat clustering, we don't have any internal cluster structure. We just assign labels. Hard clustering, we assign everything to a unique cluster. Or we can do soft clustering, where we actually have like a metric that says, you're 45% tall and 25% short, right? Something like that, which doesn't make sense in that example. But we can have like kinds of labels where you can be a member of multiple different clusters, right? We'll see this more in classification. Okay, enough of that. Lecture. If you go to your Blackboard, you will notice that on today's lecture, I've uploaded a PowerPoint. For today's lecture, I've also uploaded an IPython notebook and a comma separate values file. And this is a clustering example. The players is a bunch of football, or soccer as we call it in the United States. Football players, you can see the first one on the list is Messi. So Lionel Messi, one of the greats. Ronaldo. It's all these great players of the past, I guess, right? And they take and read that data set in. We're starting to get some warnings. I keep using the same example semester after semester, and eventually at some point warnings appear because they're changing pandas underneath me, and things that worked in the past are warning me it might not work. In this case, what we're seeing is that a couple of the columns have mixed. It didn't used to complain about that. Now it does. We look at the data. We can see we got, the name, short name, long name. There are basically 110 columns worth of data in this data set, right? And a lot of them we're going to ignore. So we look at the shape of our data, 110 columns. We look at the keys to our data. All right, well, let's go ahead and select 5 columns to do our clustering. We're just going to look at the person's overall ranking, or on a scale of 1 to 100, how great is this player, right? And their potential, how great they could be. If they're a brand new player, we're going to guess, and we're going to then say, how much are they getting paid now? How much do we think they're worth? So this is all from a Moneyball type thing, trying to figure out how we can find the best football players. So we're going to drop all the null values, so we only have useful data. We're going to create a new data frame off of that. We're going to call it data. We're going to look at data here. We've got 19,000 rows, 5 columns. We describe it. We can see that in our data, the overall is between 47 and 93. The potential is between 49 and 95. Their value is a floating point number that's a fairly large number. This is what we could expect them to contribute to our team. This is how much they're currently getting paid. This is how old they are, right? We normalize that data. We've got examples here. I think there's some stuff that's been deleted from this, so this data one is actually just normalizing to have it on a scale of 1 to 20, so we can get more differences in there. We look at our data now. We've renormalized everything, so the minimum is 1, the maximum is 10. We look at data 1. And again, everything in here is on a scale of 1 to 20. Now, we're going to go ahead and compute some random centroids, right? So we've got our data is all in the range of 1 to 10. We're going to go out there in the range of our data. We're going to go ahead, or the number of centroids we want, we're going to calculate those. So let's go ahead and start with 5 centroids. So I got to run that, run this. There's my future warning. This is going to stop working next semester. It's not too bad. We'll be able to figure that out. So each column is a centroid. Each row is a different feature. So I've got 5 centroids. This tells us where in our 5-dimensional space that centroid lies, right? Now we can't visualize 5 dimensions. So what we're going to do, we're going to get labels, look at how many data points are in each centroid. So label centroid 0 has 7,400 points. Label 1 only has 982 points assigned to it, right? We've defined a function to calculate the new centroids, so we're moving the centroids around. Now we're going to use principal component analysis to generate a 2-dimensional view of our 5-dimensional model, right? So this is going to just give us a way to plot our clusters on a flat display instead of trying to warp our brains, melt our brains using 5-dimensional visualization. Now we're going to import time. We're going to do random centroids. We're going to go ahead and start iterating on our centroids until we're finished. So let's go ahead and click on this, and we'll scroll down here. It's filling in all of our centroids, telling us what the numbers are. And we can see, looking at we're using 3 centroids in this case, of course. Come on, scroll up here. Using centroid count of 3, we can see that each step, just looking at the overall, for instance, 3.36 to 3.33, it keeps changing and changing until eventually it reaches a point where the centroids are not moving anymore. We can visualize this. There we go. Nope, get up here. It's hard to keep it. Oh my gosh, stop moving. There we go. There, our data is running. It's on iteration 35. Finally, we caught it just before it settled. Maybe we'll be able to see the other one better. Let's maximize this. Here we've got 20 centroids, right? And again, we've scaled everything on a scale of 1 to 10. There we go. So I've got plenty of centroids in here now. And of course, at each step, what we're doing is we're, starting with the centroids, we're calculating what individual data points belong to that centroid. We're assigning them. Now we're calculating where the new centroid is. We're moving everything slowly. You can see it's slowly moving less and less. Eventually around 100 iterations, because we told it to stop at 100. In this case, it gave up at iteration 81. It actually found a solution, right? Sometimes it goes all the way to 100, and things are still jiggling around a little bit, reassigning stuff to different groups. It all depends on the random seeds that you started with, and so on and so forth. Clustering will find clusters even when the data is obviously continuous in this case. Or is it continuous? We can't tell. This is a 2-dimensional projection of 5-dimensional data. It could be there are literally 20 different clusters of players in here, and they're, I doubt it. Maybe you've got clusters of great players, good players, and terrible players, right? That could make sense, but 20 different clusters, I don't think so. Okay, and that's the example. You can go ahead and download that and mess around with it on your spare time. Try different numbers of clusters, try doing different visualizations, so on and so forth, and try other data sets even with it, right? Because this is going to pull in your data set. You can do your exploratory data analysis on it and do whatever you like. We will have a clustering homework here, but it's not ready for prime time yet, so we'll get that put up next week, hopefully. So now it is time for us to stop sharing the screen and do our attendance. And then we can all go because it's already after 12 o'clock. Short quiz today. Okay, so for those of you in the room, there's the code to claim your attendance credit for today for being in person. Those of you that are online, I guess I'm in a different window. Yep, we had a few people that are online, so go ahead and contact me if you had a reason for being absent and attending virtually today, and we'll get you the attendance credit. Otherwise, people in the room get their credit. All right.